So we get started. In yesterday's class, we discussed two important concepts. What were they? Is it blurred? I read, I will concentrate on my voice. Morning. So yesterday we discussed two important concepts. What were they? One is Pascal's law. One is Pascal's law. The second is Archimedes principle, right? So those two were related to what concept? They both were related to the concept of fluid statics for yesterday, right? So when did you speak about Pascal's law? When did we speak about Pascal's law? Static is okay. So when can you give me a scenario where you know that yes, you're supposed to apply Pascal's law? Hydraulic lift is, so hydraulic lift is one of the cases. Okay, so you know that whenever there is a pressure applied at one of the points and you want it to get equally transmitted to other parts, provided it's a enclosed liquid and it is incompressible, then you think of the concept of Pascal's law. Because yesterday we solved some problems, that's right, that syringe concept and all. But when it comes to miscellaneous part, you should be in a position to know which law to apply at which point, right? Secondly, when do you know? So how do you know you are supposed to apply Archimedes principle? Solid is immersed. So whenever there is a concept of solid being immersed into a liquid, now you think logically and tell me what kind of questions can be framed. You think, let's see how you are able to think. So what are all the things that we saw yesterday? So how did we state it in the first place? When a solid is partially or completely immersed in a liquid, what will happen? Is equal to the buoyant force. Suppose you take a liquid and you immerse a solid into it. What will happen? You can see that the level of the liquid will get raised. Why is it getting raised? Because whatever is the volume occupied by the solid will displace the liquid in the upward direction. If suppose it is at the brim, what will happen? It will overflow, it will come out of it, right? So when that kind of a scenario is happening, we know that the volume of the solid immersed is equal to volume of the liquid displaced. That is a fact, known fact, because they both are replacing each other. Okay. But in a more mature way, what did you say? Weight of the liquid displaced is equal to the buoyant force, right? That is what is the mathematical expression of Archimedes principle. Let's try to thought of collecting some problems that I necessary. So concept is clear, right? I'll do some problems based on that later. So shall I move on to the next part? So with the Archimedes principle, that comes to an end of fluid statics. Now we are ready to go with fluid dynamics. Okay, let's start discussing it. So in fluid dynamics, we know that the fluids are supposed to flow, obviously. Right? When you talk about the flow of a fluid, there are two kinds of motion that you can speak about it. One is called as a, what is the name written there? Streamline or steady flow, and the second is called as turbulent flow. Okay, and what we are going to discuss is mainly concerned with respect to streamline or steady flow. Okay. Suppose you have a tube. Let's say you're doing some gardening in the morning. You connect one end of the pipe to the tap, the other end obviously will be facing the water, right? Let's say the water is flowing in that pipe. Then what will happen? If you take a particular cross section, you can say that particular cross section has certain particles of water molecules present, right? So you try to calculate the speed of those water particles at that particular cross section, and by calculating and doing that kind of a process, we'll be able to conclude whether it is a streamline flow or a turbulent flow. Okay, let's see what is a streamline flow. As the name is suggesting, streamlined. So everything is in a proper aligned manner, and second is the other name for it is steady flow. So it is having a constant flow. So when a liquid is flowing slowly through a tube, what will happen? The velocity of the liquid at any point, if it is a constant. So what is the meaning of this? The velocity of a liquid at a given point is always a constant. Then that kind of a motion is said to be streamlined motion. What is the meaning of that? Velocity of the particles, will the same particle remain there, or the position of that's the right answer. So if you take a particular cross-sectional area, so there will be a water particle present here. So let's say this point is P. Then the velocity at this point would have been what? If I call it as velocity at this point as Vp, then when this particle comes to the point A, let's say it has velocity A. There is another particle also somewhere at the back where the velocity of the particle is Vp1 at this location. But when this particle comes to point A, what is the velocity it is supposed to possess? It should possess Va. Means every particle reaching that particular cross-sectional area is supposed to have the same velocity. If this kind of a scenario occurs, then we call that kind of a motion as a streamlined motion. The first point to be noted, guys. Clear? So that's what is given C. Now let me read it out. The velocity at any point will be constant and does not change with time in magnitude and direction. Means the particles will not start moving in the reverse direction. Suppose, so they have explained it in detail of what I explained. See, consider a path ABC along which the particles are moving. Let the velocities of the particle at A, B, and C be VA, VB, and VC respectively. Okay. The velocity of the particle at A will always be VA. Consider similarly at B and C, the particles will have the same velocity, and this kind of a flow of fluid is what is called as streamlined. Right. So let us see what is the definition they have to tell us. So if the velocity of each particle at a point in a fluid does not change with time and magnitude and direction, then the flow of the fluid is called streamlined flow or steady flow. Okay, this is the important one. The line along which the particle of the liquid moves and the direction of which at any point gives the direction of flow of a liquid at that point is what is called as a streamline. So the line along which the particles are moving is what we call it as streamline. Means if you take the liquid, so liquid is going to be a continuous structure, right? If you are able to divide it into different layers like this, if the particles are moving along those particular layers, then that particular layer is what is called as a streamline. And this kind of a flow is called as streamline flow. Okay, that is how they are named. So streamline can be what? Just because the name is line, don't think it is going to be a straight line. Streamline can be a curve also. The streamline is a curve or a straight line such that at any instant. Okay. So whenever throughout physics, this is the mantra. Okay. Wherever you want to find the speed of a particle or velocity of a particle, at that point, draw a tangent. In which direction? In the direction of the motion of the particle. That's what we did for parabolic path also. You remember projectile motion, the particle was moving like this. If you want to find the speed at this point, what are you supposed to do? Draw a tangent. Tangent is basically a line. But I have to make this line as a ray. So I can draw an arrow mark this side or this side, but which one is right? There is the direction of motion of the particle. That is, it should be in the rightward direction. So you should be very clear about what you're doing. The same is the logic applied for the streamline motion also. So if you take a streamline, on the streamline, if there is a particle A, then the speed of the particle at A will be given by the tangent drawn to that particular point at that location. Is that clear? So this is the simplest thing. Okay, so having said all these things, there are certain properties that we need to have in our mind to understand what is a streamline motion. So first, what is it? Streamline may be a smooth curve or a straight line. So that's what we discussed. Second, the tangent drawn to the streamline at a given point gives you the direction of velocity, right? It gives the direction of the velocity at that point. Third important point, this is the most important point. No two streamlines can ever intersect. Why? No two streamlines can ever intersect. Why? That is not right. Intersect in the sense they need not overlap. You are trying to say overlap. That is infinite solutions. I'm saying they cannot be like this. If one streamline is like this, other streamline is like this, they cannot intersect. Okay. No, that's not it. They are in the same direction.
So in that, at that point, you can't find the velocity.
Perfect. Why can't you find the velocity? Perfect. That is the answer expected. So if you draw two streamlines and they intersect, what will happen is at that point you can draw two tangents. Means you're trying to say that the same particle is having two different directions at the same instant, which is an absurd thing. It cannot happen, right? You cannot go in two different directions at the same time unless it is split into two parts, right? So this is the most important point. So wherever this concept of the tangent giving the direction of something comes into picture, right? There, this concept will come. Similar is the case. So just to, I know it is out of context, just to give you an idea, you know about magnetic field lines, right? You would have learned that two magnetic field lines can never intersect. Why? Compass will show two different directions. Theoretically, it should show two different directions, but which is not possible. Same logic. Okay. There also you draw a tangent, right? The compass is actually a tangential surface to the magnetic field. Okay. Next, streamlines are crowded when the velocity of the fluid is moved. So if suppose they give you a diagram and they give you a crowded portion, let's say the pipe is of a varying cross section. It is something like this. It is opening its mouth like this, and you have streamlines, right? So I'm taking two different points, A and B. Now, if I'm putting a simple question, you tell me where do you think is the speed of the fluid more? A. Why is it so? Because the density is. It is something similar to what you have learned in magnetic field lines. Now, if you take magnet, what will happen? Magnetic field lines are closer near the poles and they are farther away at different locations, right? Same logic. So wherever you find more density of these kind of structures, there something will be higher. In this context, what is higher? Velocity is higher. I'll tell you. Density in the sense, I'm not talking about density of the liquid. I'm talking about the density of the lines that are there. See, for example, this room is there. This is around 300 square feet. Okay, this room. Like how many of you are sitting? 1, 2, 3, 4, 5. If I ask you the population density of this, what will you say? 5 divided by 5 members out of 300 square feet. So 5 divided by 300. So what will be the answer? 1 by 60 something. 1 by 600, 60, 1 by 60, whatever it is. Okay. If I say I dump in 100 people into this, what is going to be the value? Which one is 5? Which one is, I'll complete that, I'll come to it. Which one is 5? 1 by 60 or 1 by 3? 1 by? Right. That's what is population density. In a similar way, this is about the line density, how crowded the lines are. So don't get confused with the density of the fluid and the density of the lines. Yes. How closely lines are packed is what we call it as density. Right? I hope I'm clear with these points, right? No doubt. Guys on the other side, those are online. Any doubt?
Understood, sir.
Okay, good. So next is the tube of flow. So till now we discussed about the streamline flow. Now it is the tube of flow. So if you talk about the collection, that is a bundle of all these streamlines put together, which are enclosed in a portion of a fluid, this is what we call it as a tube of flow. The collection of all these streamlines, to put it in simple terms. So the bundle of finite number of streamlines enclosing a portion of the fluid is what we call it as tube of flow. Okay. So consider a cross section A in a streamline flow. The streamlines along the boundary of the cross section, forms the flow of the tube of flow. The velocity of flow will be parallel to the boundary. The rate of the fluid along the tube is always a constant. Have this in mind. The rate of flow of fluid along the tube is always a constant. Have this in mind. I'll prove it mathematically. But did you understand what is tube of flow? The bundle that you are speaking about, this one is what is called as the tube of flow. It's just a term. It's a technical term. That's it. Right. So the counterpart of the streamline flow is what is called as turbulent flow. So have you heard this word turbulence? Well, if you have traveled in flight, you will hear this, right? I'm not sure if you have sensed it. There will be a slight wobbling that will be taking place. So that's what we call it as turbulence. So, but here we are concerned about more of liquids, right? So turbulent flow means what? So what do you feel when you feel the turbulence in the flight? You will feel that there's something is not steady. Same logic. Just a minute. So this one, the turbulent flow is unsteady, consists of eddy currents or eddies. Don't worry about what are these eddy currents. Eddy currents are generally called as circular currents. Okay, about this in depth, you'll learn it next year in a chapter called electromagnetic induction. So here they've used that word. I'll give you a simple example. Like you take a waterfall, you could have seen the waterfall, right? How will the water fall? Once the water falls, it gets mixed with the liquid at the horizontal surface. How will you feel it? You will see some kind of spherical structures that are the circular structures that are taking place, right? That is what we call it as a turbulent. Okay. Generally, if you take the water that is flowing through the tap, example, which we took for gardening purpose, that can be approximated to a streamline flow. Still, you will find a small amount of turbulence. But for the turbulence to be controlled, what you need to do, you need to control the speed of the tap. That is why if you see the statement itself started like this, when the liquid is flowing slowly, then we can think of, we can approximate it to a streamline flow. But what we are going to deal in this chapter is completely the streamline flow. It's an ideal situation. Reason behind turbulent flow, the way the particles are moving. The way the particles are moving and they are getting clubbed with the other particles. Because the main advantage in fluid is what? Advantage and disadvantage both. But advantage is based, all these things are based on what context you want to use it, right? So what will happen? The particles are loosely bound. So what can happen? You cannot control their motion. They have random motions, right? That's the reason why you have a turbulent flow. So technically also there is a reason, something called as critical velocity, that we'll be discussing next. Okay. So as of now, please accept this, guys. Eddy currents means circular currents. If you want, you can write down the meaning of it. I'll write down the meaning. Eddy currents are generally circular currents. Here currents means water current or the fluid current, whatever you're trying to talk about. Okay, so what will happen is these eddies will absorb large amount of energy. So in a turbulent flow, what will happen is the internal friction, that is the viscosity, is going to be slightly higher compared to the streamline flow because the smoothness is not maintained. Okay, it's much greater than in the streamline flow. As I told you, streamline flow will also have, but not to the extent to which these particles exhibit. Okay, now let's see what is the difference. So in a streamline flow, what should happen? The velocity of the fluid at any point should be a constant. It does not change with respect to time, both in terms of magnitude and direction. So here what will happen? The velocity of the fluid at any point is not a constant, and obviously it is going to vary with respect to time. Both in terms of magnitude, it can happen in terms of direction alone, or it can happen only in terms of magnitude alone because of the collisions that are taking place. Okay, secondly, streamline flow, obviously, streamlines are obviously uniform, whereas streamlines in the case of a turbulent flow are not uniform. That is, the curves that you draw will be a non-uniform surface. Third, so this flow obviously does not form any eddies and vortices, so need not get into those technical details, they've given it. So this is disordered flow, growing eddies and vortices. Okay, 4.3. Velocity of the fluid is less than the critical velocity. This is what I told you. So this critical velocity is a number which will tell you whether it is a streamline flow or a turbulent flow. So that is how they will test you in the exam. But till now, whatever we discuss is for the knowledge. Okay. Fourth one, velocity of fluid is more than the critical velocity. Fifth one, for a streamline flow, Reynolds number is less than 100, whereas for a turbulent flow, Reynolds number is, sorry, not 100, 1000. It's less than 1000, and here it is greater than 1000. Now let's see what this critical velocity has to tell us. That's what I told you, need not worry about. Okay, so let's get into the concept of critical velocity. So what is it? The minimum velocity at which, what are they trying to say? The minimum velocity at which the flow of a liquid changes from laminar. Laminar means, laminar is something like a plane sheet. Your paper can be called as a lamina. The paper on which you are writing is a lamina. So if you take the series of lamina or you try to draw a set of parallel lines on that, that's what you can call it as streamline. Okay, here they use the word called as laminar. So the minimum velocity at which the flow of a fluid changes from where? Changes from laminar, that is a streamlined, to a turbulent state is what we call it as critical velocity. So there is a basic definition. Okay, so this is the minimum velocity that is required where the water which was having a streamlined flow will immediately get converted to a turbulent flow. So that is the minimum value required for this transition to take place. Or what value can you say? You can state the same thing in a different way also. It is the maximum velocity of the fluid in a tube for which the flow remains streamlined. Means if you try to increase the value beyond this, it will become a turbulent flow. Try to think about this. Guys, I hope it is not confusing, right? Minimum and maximum. Are you clear? Suppose I give you in an MCQ or something, you will be able to answer it. So look at the definition. So the minimum velocity that is required for what to happen? Streamlined motion to get converted to a turbulent motion, or the maximum velocity in which a streamlined motion can be maintained is what we call it as critical velocity. So if the velocity of the liquid is less than its critical velocity, obviously the flow is going to be streamlined according to the definition. The velocity is above the critical velocity, the flow changes to turbulent flow. So critical velocity will vary from liquid to liquid because of its property, because of its density, the way the particles are there. So its value will be more for highly viscous liquids. So what do you mean by highly viscous liquids? Suppose I give you an example like this. I'll give you water and I'll give you honey. Which one is more viscous? So that's what they're trying to say. So its value is more for highly viscous liquids. Means if you have a highly viscous liquid which you want to convert it into a turbulent flow, you need to supply more amount of this critical velocity is what they're trying to say. Am I clear? So there is something called as a Reynolds number. Okay. For this Reynolds number, you need to understand a concept called as coefficient of viscosity. But viscosity is, according to our schedule, we'll be discussing only the next week. So this Reynolds number alone, I'm holding it up. Okay. So with the knowledge of streamlined and turbulent flow, it is sufficient enough for us to understand two important things in this chapter for ideal fluids, where one is called as equation of continuity and the second is called as Bernoulli's principle. Okay, that's what we are going to discuss next. Shall I proceed? Students, those who are online, am I clear?
Yes, sir.
Yes, sir.
Okay. So please write down the heading. This is a very, very important derivation. I want you all to write it along with me. Okay. So what is the name of it? It's called as equation of continuity or principle, PLE, not PAL, principle of continuity. Okay. So let's try to read the statement once. What are they trying to say? When an incompressible and non-viscous fluids flow in streamlined motion through a tube of what cross-sectional area? Non-uniform cross-sectional area. Means its area is changing from point to point. Then what will happen? That then at every point of the tube, the product of what? The product of area of cross-section multiplied with the velocity at that particular point will always remain a constant. This is a statement you need to have in your mind. Don't read it without understanding. So what are the two things you need to have when you need to apply this concept? First thing, first important thing, you need to have an incompressible fluid in the first place, and it should be a non-viscous. And the liquid is supposed to have what kind of a motion? Streamlined motion. It should have a streamlined flow. All these concepts put together, all these keywords put together, you can call it as an ideal fluid. Because if you increase the speed, it can happen. Because the particles will move with a relatively greater speed, where they will collide inside and start developing angular momentum. I'm not able to get them. Depends. It depends. Like we can't conclude this like that. It depends on where the collision is taking place. It is like you have to diagnose the situation and then answer. I cannot generalize. It depends on that particular scenario with respect to that particular fluid and that particular tube. All those parameters come into picture. Okay. So, yeah, what were we discussing? Ideal fluid. So, what did I say is an ideal fluid? When you talk about an incompressible, non-viscous, and a liquid which has a streamlined flow. Okay. So, if all these concepts come together, we call it as an ideal fluid. if that is flowing through what kind of a tube? A tube which has a varying cross section, means it's of non-uniform cross-sectional area. Then what will happen? Then you can say that the product of whom? Area of cross section. Area, which area? It is the area of cross section multiplied with the speed of the fluid at that particular point is always a constant. I told you I'll prove you something, right? There is something which I want to connect it with the previous topic that we discussed. In the tube of flow, if you see the last word, the rate of flow of fluid. Can you see that? The rate of flow of fluid along the tube of flow is always a constant. Okay. So have this point in your mind. Please write down this word, rate of flow of fluid. Just write down this keyword. Okay. They can confuse you in the exam by putting this word. Rate of flow of fluid. Because I'm believing that you're writing on the other side, right? Everybody. Right. Every fluid will have this concept. Comparison. If you take two fluids, you can say one is relatively less viscous compared to. There are certain situations where you can control the experimental factors to make it a streamlined motion and ideal. Okay. So what did I tell you now? What is the keyword I asked you to write? Rate of flow of fluid, right? So tell me what is the meaning of this word rate of flow of fluid. Rate means what? Rate is something which is varying with respect to time. So rate of flow is defined by what? It is defined with the amount of volume that is flowing per unit time. That is the rate of quantity of a fluid that is flowing through a particular cross-sectional area is always a constant. So here V stands for what? Not velocity. V stands for volume. The amount of volume flowing per unit time is what is technically called as rate. Generally, it is represented with the symbol Q. If some books only represented with the rate of flow of liquid. Now let's think of one logic. Here, what did they say? They told when you have an ideal fluid, the area of cross section multiplied with velocity, right? Area of cross section is what? It's measured in meter square. Velocity is measured in meter per second. So meter square into meter is meter cube per second. Meter cube is a measure of what? Volume. So this product of area of cross section and velocity is indirectly the rate of flow of fluid. So what they will do is in the exam they will directly ask you what is the rate of flow of fluid at that particular point. They would have given you area, velocity, everything, but what will happen? You will get confused of not knowing what it is. Your work is only to take these two parameters and multiply and tell the answer. Am I clear, guys? So there are certain questions of that sort. Any doubt? Clear? Can I rub this? Okay, I've written it. Huh? So what is that we need to prove this? Our job is to prove. Given, provided the certain conditions are given to us. So I have a tube of varying cross-sectional area. Here the area is A1 and here the area is A2. Okay. And let's say the volume, sorry, the speed here is V1 and the speed on the other side is V2. What is it technically supposed to happen? A1 into V1 should be equal to A2 into V2. That is what the statement says, no? Area of cross-section multiplied with the speed at that particular point, A1 into V1, should be technically equal to A2 into V2. If suppose I take any other cross-section in between, area is A and the velocity is V, I can say A into V is always a constant. That is the mathematical meaning of the statement. This step. Throughout the area of cross-section. So if suppose I take a streamline like this, you take any particle on the same cross-sectional area, they will have the same velocity. That is why I'm saying the velocity of the liquid at that point is a constant. That's what the statement says. No, the product of area of cross-section and the velocity of the flow remains a constant. That is what the statement says. That is what we need to prove.
another particle, when it comes to that point V1, it will have same
velocity V1.
A.
It will have the same velocity as V1. V1, but the area of cross section is not changing. No area of cross section. They didn't say area of cross section at the same point is changing. It is not a dynamically changing area. The area of cross section of the tube is fixed at that point. And according to the definition of streamline flow, any particle reaching that area of cross section at that particular instant will have the same velocity. So that is why the product of these two is always a constant.
So the constant doesn't depend on the particular particle.
We don't discuss all those things. If these things are given to, we will not get into those details because if I take all those parameters, then I have to take the viscosity also into consideration. We will not get into those. As I told, yeah, liquid is ignored provided it is given that it is an incompressible. That's it. It can be of any nature that we are not concerned about, and it should have a streamline. Then we can apply. Density matters. Density matters, but it gets cancelled. Because when I say incompressible, what did I say? Incompressible, indirect meaning is density is a constant. So that is the meaning. Because this concept works on the conservation of mass. Okay, let me explain what it is. So, see, maybe after the derivation you will understand. Consider a liquid flowing through a pipe of varying cross-sectional area as shown. The liquid enters with velocity. Somebody has asked this. Okay. Consider a liquid flowing through a pipe of varying cross-section as shown. The liquid enters with velocity V1 at point X and leaves with velocity V2 at point Y. Okay. Let D1 and D2 be the density of the liquid at X and Y. Will that be possible? It is incompressible, right? They are taking it for the sake of assumption. Okay. Let D1 and D2 be the densities at point X and Y. Okay. Now, volume of the liquid entering at point X1 will be how much? What is the volume of the liquid that is entering? Rather, I'll make it very simple. Instead of asking you the volume, I'll ask you what is the density? What is the mass of the liquid that is entering? Density to volume. So, can I say the amount of mass that has entered here should be the amount of mass that is leaving here? Or else what has happened? Then the liquid will be compressible. The liquid would have been compressible. So density is a constant and the volume is also a constant, so that the product of these two, which gives you an important parameter called mass, is also a constant. So this is a phenomenon which works on the principle of conservation of mass. So they can give you option: conservation of density, conservation of volume, or conservation of mass. The most appropriate is conservation of mass. Okay. So what is going to be the mass that is entering here? M1 should be equal to M2. But M1 is equal to density 1 into volume 1. Don't get confused with this V1. Is equal to D2 into V2. Right? D1 into what is the volume that is entering there? What is the volume that is? So for the volume, what I will do is, I will say this is happening in a time of delta t. So in delta t, let's say V1 amount of volume is pushed in. In time delta t, what should happen? The same amount of volume should be pushed out. Okay. So in how much time? In the same. So I'm trying to understand the concept here. I'm trying to analyze the situation from 2 point of views. Which point of view? One is at point X and the second is at point Y. At point X, what is happening? There is a certain amount of volume that is coming as an input. So if the liquid inside is supposed to be incompressible, means what should happen? The volume of the liquid that is there inside the tube should be a constant. If that should be a constant, how much ever has come in should be the same amount leaving from the other side. And this all process should happen in what instant of time? Same instant. In the same time interval delta t, all this thing is supposed to happen. So d1 into what is the value of v1 guys? Volume is what? Basically area multiplied with the distance to which the liquid has got transmitted. So can I write it as a1 into what is the distance the liquid would have traveled at point x in time delta t. V1 into delta t, is it not equal to d2 into A2, area of cross section? I'll finish that and come. A2 into V2 into delta t. So what you get cancelled? Delta t and delta t are gone. D1 and D2 are gone because they are same. But the area of cross section and velocity, they are not same at both the points. So A1 V1 is equal to A2 A. So this is the meaning. Yes, sir. Where did I write mass into this? I wrote density into volume. I wrote both the masses are same. A1 into V1 is the rate of flow of liquid. Just now I told you. A1 into V1 is volume per unit time, rate of flow of liquid. Because area is meter square, velocity is meter per second, meter cube per second. You're able to understand? Which one? Which V1? Huh? So this is velocity. This is velocity. I'll use a different symbol. This top one, this one. A1 V1 into D1. Strike it off. Let's not worry about it. You just follow the method which I explained. So two important points to be noted. What are they? One is D1 into V1 is a constant, and the second one indirectly means mass is constant. So this law, this principle is based on the conservation of mass. Please don't forget it. Okay. So this particular concept does not depend on which end is at which height. It can be of any shape. See, for example, if I take this water bottle, you are able to see it has a varying cross-sectional area. Right? So A1 into V1, the speed of the particle at this point, should be equal to A2 into V2. If suppose you want to find it at this point, then you need to know this area multiplied with the speed of the particle at this point. If you try to calculate all the values according to this principle, mathematically they should give you the same number. That is the meaning. Can I proceed to the next part? Still this is if even if it is showing another influence of gravity, yes, it's the same thing. But if you want to take the effect of gravity into consideration, for that only we have another principle called as Bernoulli's principle. Okay. So let's see, it's a slight difference. Bernoulli's principle, what happens when you talk about a non-viscous incompressible fluid? Can I still say it's an ideal fluid? It's still an ideal fluid. When you have a non-viscous, incompressible and irrotational fluid, when you say irrotational, the particles do not exist, the particles do not experience any angular momentum. That is the meaning. Okay. So when you have this kind of a fluid, what should happen? Read the statement. The sum of pressure energy, potential energy, and kinetic energy per unit volume. I repeat. Sum of the pressure energy, potential energy, and kinetic energy per unit volume at every location is the same. I'll come to the pressure energy is pressure. Okay, I'll come to that point. Right? So I want you to write it down. Though it is there in the notes, please write it down for the sake of practice. These are all very important concepts. When a non-viscous and incompressible fluid, incompressible and irrotational fluid. When a non-viscous, incompressible and irrotational fluid flows steadily, comma, the sum of the pressure energy, kinetic energy, and what? Potential energy per unit volume. potential energy per unit volume of the fluid remains constant at all points in the path of the flow. At all points in the path of the flow. Or remains constant at all points in the path of the flow. Okay, this is the theoretical statement. So mathematically, how are we supposed to write it? So if suppose you have a tube of varying cross-sectional area, inside which there is an ideal fluid that is flowing, right? And the tube is kept in such a way that one end is at a height h1 and the other is at a height h2 with respect to the ground. Okay, when this is going to happen, then you can say the pressure energy per unit volume. Pressure energy per unit volume is pressure only. Why it is so, I'll explain over. Plus kinetic energy, that is half mv square per unit volume, plus potential energy. What is it? mgh per unit volume. All these things are constant. If I have to write it in a better way, P plus half into what is mass divided by volume? Density, mass density. So rho v square plus again mass divided by volume plus mass density into rho gh is always a constant. That is what they are given here. Okay, this is a mathematical expression. And yes, you can expect the derivation if it is subjective. This derivation will definitely be asked. Or you can expect at least a problem. Generally, when there is a 5-mark problem, right, 3 marks will be for derivation and 2 marks will be for problem, or 4-1. They will divide it like this. Okay, so this is a very, sorry? No, it's not, I have not yet started the derivation. This is only a statement. This is what we need to prove. If you look at it like a mathematics, because that's what the statement is. The pressure energy, kinetic energy, potential energy, all these things per unit volume is a constant. Okay, it is not only potential energy per unit volume. Don't take it in the wrong sense. Not sure if the confusion is used properly. The sum of the pressure energy, kinetic energy, and potential energy, all those things put together by whole volume. Because pressure energy is nothing but work done by pressure. Pressure, if you take pressure and energy per unit volume, it is pressure. Okay. That's what I told you. I'll explain how it is. Okay. So before I get into the derivation, I want you all to note down this point. Student learn thermodynamics and chemistry, right? First term is over. First term you didn't learn it, right? Suppose, let us say there is, so there is only a pressure energy. I'm going to explain what is the work done by pressure. Don't get confused between this and the incompressible fluid. This is a derivation which I'm trying to show you for the mathematical expression. So let's say this is covered with a piston. Okay. And you're applying a force from the top. So will the subject get compressed or expanded? Compressed, obviously, because you're applying a pushing force. And let's say the area of cross section A is A here. And let's say in time t, the particle has got displaced by a distance x. The fluid has got compressed and the piston has moved by a distance of how much value? The distance of value delta x. Okay. So what are the basic definition of work done? Say here I'm assuming that the force is constant. What will happen when it is variable? We'll see it in thermodynamics. Okay. So what is work done basically? Simplest definition is F into delta x into cos 0. So F into delta x. But what is F in terms of pressure? Pressure into area multiplied with the displacement. So, but what is area of cross section multiplied with displacement? Is it not volume? So, is it not the amount of compression that has taken place? So, this is the work done by the force, right? This is not the work done by the pressure. This is not the work done by the pressure. Because you're applying a force, indirectly what are you doing? Force applied on a unit area is nothing but pressure. So can I call this as work done by constant pressure? Because I took force to be constant, force is constant, pressure is also constant. So work done by constant pressure. We know the fact that energy is a capacity to do work. So work done by constant pressure, P into V or delta V. Or you can take P into delta V also. Here, V, by writing V, I'm trying to say what is the change in volume that has taken place. But you have to understand that the product of pressure and volume is what? So delta V or V both mean the same. V is the volume to which the liquid has got compressed or the fluid has got compressed. Okay. So work done by constant pressure, can I call it as pressure energy? Because we know work done by any force will get stored in some form of energy. Here the work is done by pressure. So it will get stored in the form of pressure energy. Now what does Bernoulli's theorem tell us? Amount of pressure energy per unit volume. Volume and volume will get cancelled. So what is it? It's a pressure. That is the reason I told you amount of pressure energy per unit volume is pressure. Got it? So this is actually not a part of the syllabus. See, work done. You see, whenever you take your science textbook and see, whenever you are calculating energy, right, you will always calculate work done. So once you calculate work done, that work done is what is going to get stored in some form of energy. The only question that you're going to ask is that work is done by which force. So based on that, you will talk about the name of the force. For example, the simplest concept that I can explain again is if an object is thrown against gravitational force. So mg is there, it has got displaced by distance h. So force multiplied with displacement is actually work done. But this mgh, what do you call it as? What potential? By. Because it is work done by the gravitational force. So whichever force is there, that is added as a prefix to that word energy. Okay. Not in all contexts. That doesn't mean kinetic means kinetic is a force, not it. Okay. So mgh is gravitational potential energy. Here it is pressure. So pressure energy per unit volume is pressure. Guys, I hope you are clear, right?
Yes, sir.
So shall I proceed with the derivation for Bernoulli's theorem? Yeah. It's slightly complicated. Please concentrate. Okay. So consider an income. The same logic again. Consider an ideal fluid, and this ideal fluid is passing through a varying cross-sectional area. Accepted? So when it is passing through a varying cross-sectional area of areas A1 and A2, and let's say the velocity of the fluid entering is V1 and the velocity of the fluid when it is leaving is V2. We have taken the end points, the extreme points into consideration. This is the diagram. Any doubt in this? Diagram is simple, right? So the height is H1 and H2. Right? Now, tell me the logic. Why is the liquid flowing from 1 and 2? So you tell me the logic. Will the liquid flow from left to right or right to left? Why? Since there is a difference in the gravitational potential, that is one logic. Due to which, can I say there is a pressure difference that is going to exist? So whichever is the direction of fluid, you can see if I give you the direction of flow, it is easy for you to find out which side has greater pressure. Let's say water is flowing like this. I do nothing. If I put it like this, what can you say? The pressure at this side is more compared to this. That's a simple logic, right? So that is why they have told something like this. P1 and P. Just because they have given arrow marks, don't get confused. Okay. Now see, irrespective of heights that are present, I already told you that the equation of continuity is applicable. So A1 into V1 is equal to A2 into V2, where A1 is area of cross section of the entry, A2 is area of cross section of the exit. And V1 is the entry speed and V2 is the exit speed. Let me call this as equation number 1. Okay. So in a small time dt, what will happen? The mass of the fluid at the beginning is ρ1 into A1 into V1 into dt. So how did they write it? This I already showed you. What is the mass of the liquid at the entry? Density into volume. Density here is rho. Volume is area of cross section multiplied with the displacement. Displacement is V1 into dt. So rho 1 A1 V1 dt. Does that make sense? So rho 1 A1 dt, and at the end point is going to be rho 2 A2 V2 into dt. Now the important question is, in this derivation, what we are supposed to do is, since we are concerned about energy, we need to speak about the works. Okay. So here the work done by which force is getting converted into which force is what we need to see. Okay. So work done on the fluid while entering, can I write it as P1 into A1 into V1 into V2? So how did we get it? P1 into A1 is what? Force. Force into V1 into dt is displacement. Are you guys able to understand? So P1 into A1 is going to give us the force, and V1 into dt is going to give us the displacement. So that is the work done at the entry, right? So this is the work done by the pressure at point 1, right? The work done by the fluid at the exit, what is it going to happen? In a similar logic, F2 into A2 into V2 into dt. Guys, any doubt at this point? Is everyone clear? Right? So this is what is going to happen. Now, what is going to be the total work done, that is total work done due to the pressure difference? So here, the logic that I am able to understand is liquid is able to flow only because of one reason. What is it? There is a pressure difference existing between whom? Between the first point and the second point. Right? Between those 2 points, there is some amount of work done by the pressure. What is it going to be? It will be the difference in the work done by the pressure at point 1 and pressure. So that difference in pressure is what is making the liquid flow. So try to understand. Just because they are using total work done, what the common mistake that we will do is we'll try to add the flow. So total work done is because of the pressure difference. So P1 A1 V1 dt, that should come first because that is having higher pressure, minus P2 A2 V2 dt. Is that right? Any doubt in this? Guys, are you clear? Subraj is clear? Right? Next. What is the work done by the gravitational force at the beginning? So it is the mass of the liquid that has got displaced where the height is h1. So it is mg h1. What is the work done by the gravitational force at second point? mg h2. So what is the net gravitational work done? Again, I can say due to the pressure difference. So the pressure difference itself is occurring because of the difference in the gravitational potential. So can I say that the difference in these two heights are able to observe? So this height is what is the cost for this liquid to flow. So what is the total work done by the gravitational force? It is mg h1 minus mg h2. That is mg into h1 minus h2. Next. According to the work energy theorem, the total work done by all the forces put together should be equal to, according to work energy theorem, the sum of work done by all the forces should be equal to change in kinetic energy. That force can either be conservative or non-conservative. Fortunately, here everything is conservative because gravitational force is conservative, and here we are taking ideal fluid, so there is no viscous force in picture. Right? So if you're clear till this step, please write it down. Please write down in the same way that they are given. Sure. So you start from here. You need not write the whole theory. You start from here. So as I told you, there is a very, very important derivation. I'm suggesting everybody to write it. So while writing, if there is any doubt, please ask. You write it till mg into h1 minus h2 and stop. After that, I'll explain. Should I proceed? Done? Right. So you're writing down any doubt? You guys wrote it with clarity only, right? Okay. Now listen. So work done by potential energy plus work done by the gravitational force is equal to change in kinetic energy, right? So what is the work done by the pressure energy? P1 A1 V1 into dt minus P2 A2 V2 into dt plus mg into H1 minus H2 is equal to, here you need to be careful, difference is final minus initial. So here we wrote 1 minus 2, whereas here it will be half m1, sorry, m2 v2 square minus half m1 v1 square. Am I clear with this? No. I'll do that change. I'm going to do that. So a1 into v1 is equal to a2 into v2. We need to have this in mind. Similarly, we know that it works. So a1 v1 into a2 v2 itself works on the principle of conservation of mass. So can I say m1 is equal to m2? Can I write it as the density of the substance, that the liquid which is flowing, multiplied with what? With the volume. Volume is a1 v1 into dt. Does that make sense? Did you understand what I wrote? Rho is the density into volume. So in the place of volume, what did I write? Area multiplied with distance. So area is A1, distance is V1 into dt. Is that step clear? This is the most crucial step. Now what I will do is, I will use these two concepts in this expression, so that things become simple for me. So P1, A1 V1 dt, I'm keeping it undisturbed, minus P2, instead of A2 V2, can I write it as A1, sorry, can I write it as A1 V1 minus P2 into A1 V1 into dt plus, in the place of m, can I write it as rho into A1 into V1 into dt into G is already there into H1 minus H2 is equal to half into, I will take m outside. What will I write? Rho A1 V1 dt into V2 square minus V1 square. Any doubt? Any doubt? So did you understand why I took the mass outside here? Why did I take it out? Because it is the same value, right? Now what parameter will get cancelled? You see, one, everything will. A1 V1 dt is gone. A1 V1 dt, A1 V1 dt, A1 V1 dt, and A1 V1 dt is gone. So what is that you are left out with? P1 minus P2 plus rho g H1 minus rho g H2 is equal to half into V2 square minus half into V1 square. So taking all the negative parameters to this side and the negative parameters on the right to the left, what will I get? P1 plus rho g H1, P1 plus rho g H1 plus half rho V1 square is equal to P2 plus rho g H2 plus half, I missed a rho here. So I wrote it. Mass is equal to density into volume now. Got it? So half rho into V2 square. Does it make sense? So pressure at point 1 plus rho g H1 plus half rho V1 square is equal to pressure at point 2. Look at all the parameters 2, 2, and 2. Similarly, if there is a third point, what will you get? You will get 3, 3, and 3. That is why whenever these kind of things are occurring, what can you conclude? Pressure plus potential energy plus the kinetic energy, all those things divided by unit volume, I can conclude it to be a are you able to understand? So please write. You take out everything common. See, the first one, what will happen is it not A1, B1, the first bracket that I put, can I say A1, B1, dt is a constant, right? So what will you be left out with? A1, B1, dt into P1 minus P2. Plus, here already A1, B1, dt is there. So A1, B1, dt into rho g into H1 minus H2 is equal to right side, you already have a rho into A1 into V1 into dt. So A1, V1, dt on all the sides will get cancelled. Okay. So not rho and A1, V1, it is only A1, V1 into dt that will get cancelled. I just skipped 2 steps. There's one of the toughest concepts in this chapter, but you are complete. Sure. Which step? I'll do one thing. Will this work? Yes, velocity. Students, did you copy? A1 is area of cross section. Equation of continuity. The previous theorem. The previous principle told us that whenever you have an incompressible fluid, the product of area of cross section and velocity is always a constant. A1 into V1 into dt is mass. The dt will get cancelled in the previous derivation. Instead of dt, I use delta t. So I hope you are done, guys, right? The math sir is waiting. Can I close this? Students, you can leave.
Thank you, sir.
Thank you, sir. Thank you, sir.